recording from whatever, but that's what I'm going to do today, just introduce the logarithms as if, because I kind of gave you a little chance to catch up and maybe understand a little better what I started to do last Monday. So basically that's section 5.3, logarithms. And really sections 5.3 and 5.4 both dealing with logarithms, the properties of logarithms. 5.3 introduces the logs, and 5.4 gets into more properties. And the next is going to be equations and word problems. But so I'm really covering those two, 5.3 and 5.4, simultaneously, because we'll just list them same way. And that's your homework 12, right? It's based on these two sections. That leads to quiz 9? 8? Okay. All right, so again, the way we define the logarithm is the inverse of the exponential function. And the way we got the graph, because we already understood what the graph of the exponential function was. So we did the logarithm by flipping it over that line y equals x, so it had the x-intercept of 1 and all that good stuff. So if this function is f of x equals a to the x, then this function right here, f of x, is log base a of x. Now again, the properties were the domain is strictly positive. So I'll be asking you find the domain of this logarithmic function. So just like with the square roots, we'll take whatever's inside the logarithm and set it to greater than 0 and solve for x and things like that. The range is just all real numbers. It has a vertical asymptote, would be the x-axis. I'm sorry, the y-axis. So that's the vertical asymptote. It has the x-intercept of 1, 0. So this is the basic properties, and the idea is when we see log base b of a, it's really asking us to what power to raise b in order to get a. So again, b is the base and a is the answer, and the log itself is the exponent. So log spits out the exponent. Just like opposite of the exponential function. Exponential function takes exponents, gives you, what just happened? Did I just hit a, there we go. The exponential function takes in an exponent, gives you some kind of an output. The logarithm does the opposite. We'll take the output and we'll give you an exponent back, given the base. So another way to say log base a of x equals y is equivalent to saying that a to the power y equals x. The base stays the same. The logarithm, the value of the logarithm is the exponent. The input of the logarithm is the value in the exponential function. So again, x's and y's are kind of flipped if you think from the inverse point of view. So a few examples. I'll just give you a few numerical ones, and we'll see whether we can guess the answers. I mean, we should be able to evaluate. So some examples: log base 3 of 9. So again, all I'm asking, to what power to raise 3 to get 9? 2, right? You'll agree with that? So the value of this logarithm is 2 because base raised to whatever's on the right side equals whatever's on the inside. So because 3 squared equals 9. So that's what logarithms tell us. They tell us to what power we need to raise the base to get whatever's number on the inside. Is that okay? I can ask you log base, I really don't know, log base 5 of 1/5. To what power to raise 5 to get 1 over 5? So you have to ask yourself, well, which, negative 1. So you need to take the reciprocal. So the answer here is negative 1 because 5 to the power negative 1 does equal 1/5. Is that okay? How about log base 10 of 1,000? What do you think that equals to? 3. Because 10 cubed is 1,000. So these statements are equivalent. The left side, all of these guys, that's called the logarithmic form. Whatever's on the right side is called exponential form. I'm missing what? Oh, yeah, that's fine. And we should be able to go freely between one and the other. I can give you an expression written in logarithmic form. You should be able to flip it around into exponential form and vice versa. So yeah, how about log base 7 of, well, let's do the easy one, 49. 2, right? Let's do an even easier one. Log base 7 of 7. 1. To what power need to raise 7 to get 7? Good. How about log base 7 of 1? 0. To what power need to raise 7 to get 1? Actually, when you look at this logarithm, it doesn't matter what the base is. I can put any base here as long as, well, you guys told me 0, right? And I wrote 1. Well, just me being silly. So it doesn't matter what the base is. Log base 17 of 1, log base 27 of 1, log base 1.7 of 1. The answer is always going to be 0, right? To what power to raise any number to get 1? The answer is 0. Now, the bases here are positive, just like with the exponential function. So there are some restrictions, but any base of 1 will give you 0. How about log base 7 of 7 to the power 5? What do you think that equals to?
Why does 7 to the 0 give you 1?
What?
7 to the 0th power?
Yeah. Isn't that anything to the power 0 equals 1?
Yes, sir.
Why is 7 to the power 0 equals 1? That's a good question. I mean, some of you just know that anything to the power 0 equals 1. Why is that? Who can prove that? Who can prove that? Because it has to be. Well, why does it make sense then? Who wants to prove this? Respect points are on the line. Well, so that's kind of counter. I mean, because, well, the reason why it crosses the graph is because of this. Okay, but yeah, you see the connection, but we use the fact that it crosses the graph, the graph crosses the y-axis at 0, 1, because we know that anything to the power 0 equals 1. Now the question was, why is anything to the power 0 equals 1? Well, let's review some rules of exponents, because we'll need rules of exponents in this section. So we're not really wasting time at this point. Exponents. So we have the, the product rule for exponents. If you take a number to the power n times the same number to the power n, what do we do with exponents? Add them together. So the product rule. M plus n, we add exponents. Then we have the quotient rule. Only works with the same base. Right. Now, if you have 3 cubed times 5 cubed, who cares? It's just 3 cubed times 5. Quotient rule, if you have a to the power m over a to the power n, what do we do with exponents? You subtract exponents, right? You reduce your fractions if the bases are the same. We subtract exponents. And then we have the power rule. So it's a to the power m raised to the power n. What do we do with exponents? Multiply them. Right? Now, do these rules make sense? Why they work in such a fashion? Do we need to prove those so you understand why we multiply? Because, I mean, if this is a squared then cubed, then this is a squared, a squared, a squared, and each a squared is 2a, so it's a, so it's 6a's. While here, if it's a squared times a cubed, it's 2a's followed by 3a, so that's 5a's, right? So you add powers. Okay, so now also, please tell me this question. If you have a fraction of the form, if you have a fraction of the form a smiley face over a smiley face, meaning numerator is identical to the denominator, what is that fraction equals to? 1. Okay. So, for example, what is your favorite number?
07.
Well, pick anything else. 47. Let's say I have 7 to the power 47 divided by 7 to the power 47. Do you agree that equals to 1? Yes. But the rule tells me if I'm dividing, I have to subtract exponents, right? And 47 minus 47 is 0. So 7 to the power 0 has to be 1. So that's why anything to the power 0 equals 1, because that, you can play that little game. So basically you're dividing same base with the same powers. So you subtract exponents, you get 0, but the ratio should be 1, because you're dividing two identical. Okay. Anyway, so this is why anything to the power 0 equals 1. So that's why that base is almost irrelevant in this case. So anything of 1 will equal 0 then. How about this one? Let's go back. Log base 7 of 7 to the 5th. What do you think that equals to? 5. It's almost a trick question. To what power I need to raise 7 to get 7 raised to the power 5? Well, 5, right? Because that's what the question is. To what power I need to raise 7 to get 7 raised to the power 5? Well, the answer is 5. It's almost... Now let me try this one. How about 7 raised to the power log base 7 of 5? What if I go that crazy? What do you think this equals to? What? Yeah, so this is kind of an exponential thing. You have a 7 raised to the power log base 7. 5. So yeah, these two bases match, really. 5. Who can explain that to me? You just guessed? Because forget about this first 7. Just focus on log base 7 of 5. Can you tell me what it is numerically? Say no. No. Because you do not know to what power you need to raise 7 to get 5, right? But the value here log base 7 of 5 is some magic number such that if I raise 7 to that magic number, I get 5, right? Well, I'm raising 7 to that magic number. So I'm getting 5. Because this thing is the power that you need to raise 7 into to get 5, right? Log base 7 of 5 tells you to what power to raise 7 to get 5. Well, here I'm raising 7 to that power, so I better be getting 5. Because that's what log base 7 of 5 is. It turns 7 into 5, and I'm raising 7 to that power now. Does that make sense? This one is a lot trickier than the first one. First one, yeah, that makes sense. Now, there is a special name for this too. We're going to have them as properties. These are called inverse properties. Because look, if I have these two functions, f of x equals a to the power x, and g of x equals log base a of x. Here are the two functions. Now, if I take the composition g of f of x, so it's this way. So that means log is my outside function, a to the x is my inside function. So I'll end up with log base a of a to the power x. Right? That would be the composition. And this is kind of like that example. The bases match, log base a of a, and then some power, and that's what I have here, log base a of a to some power. Now, we were able to reason to get the answer. To what power I need to raise a to get a raised to the power x? And the answer is x. Right? Or you can always say, well, that's a composition of a function and its inverse, so it should better be x without even understanding what those functions are, because you're composing function and its inverse, it's always going to be x. Definition of the inverse functions. So that's why if I go the other way, if I take the composition f of g of x, right? So f is the exponential function, and g is the logarithmic function. So we get something like this. This would be composition the other way. But again, by the properties of inverse functions, that better be x. So it is x, because it's the composition of function is inverse. So you can always say that. So this is another way to understand why 7 raised to the power log base 7 of 5 equals 5. It's a composition of a function and its inverse. You're just getting the x back. So they kind of cancel each other. Does that make sense? So you can always think of these two examples as the compositions of a function with its inverse. So they just cancel each other, and you're going to get your input back. You get your x back. How's that? So some properties of logs. So again, let a be positive, a not equal to 1, and also, I don't know. Yeah, that's about it. Just like with the exponential function. So we have the following properties. If I have log base a of 1, that is 0, as we just discussed. To what power I need to raise a to get 1? The answer is 0. So regardless of the base, that's going to work. The second property, log base a of a, that equals 1. To what power to raise a to get a? Well, 1. Nothing changes. Right? And then the last two, these are your inverse properties, log base a of a to the x, that equals x, and a to the power log base a of x also equals x. Okay. Is that all right? Now, a while back, we discussed these two equations. And we had no problem solving the first one, x equals 3. But we did not know how to solve the second one. But we do have logarithms now. So really, x equals log base 2 of 7. If I rewrite this exponential expression in the logarithmic form, it'll equal that, right? 2 becomes the base, 7 becomes the input, the exponent becomes the output. So in order for me to solve this equation, I have to evaluate log base 2 of 7, which is again the same question, to what power to raise 2 to get 7, and that didn't get us very far as solving this equation. So I still have a whole new logarithm to compute that I don't know how to compute yet. Now, our calculators are very limited as far as computing log base 2 of 7. We do not have a log general base button. Some of your fancier calculators, you can dig deep in there and you can find that ability, but the way I'm operating here, and I won't teach you how to do that. I shouldn't have even told you that that's possible. But our calculator has only 2 buttons that kind of logarithmic. There is clearly a LOG, a log. Locate that one on your calculator, the log button. And look what it says right above it. And it should say 10 to the power x, right? The way your calculators are laid out, the button and whatever says above it are usually a function and its inverse kind of a pair. So if 10 to the x is the inverse of whatever the button you're looking at, then this means that this log has base 10. So if you see a log button, that implies base 10. Okay, so I can actually do this. The 1000, we did compute log base 10 of 1000. We got 3 as an answer. So if I hit log, it gives me 3. So the log implies base 10. So when you look in your book and you're going to work on your homework, every time you see a log without a base, that implies base 10. And you can use a calculator, and that's actually a good log. We'll call it the common log, base 10, because we like base 10. Okay. There is another. What? Yeah, but it's not really a calculator. It's a. Yeah, well, that doesn't count. Okay. Then there's another kind of a log button, is the ln button. If you look right above it, it says e to the x. So that means this is a logarithm with base e. So we like that logarithm. We'll call it natural logarithm. So every time you see ln, that implies base e. So I can compute a lot of problems now that play with the base e. So if I want to compute, what is the natural log of 15, I get that, 2.708. That means if I take that number e that we discovered last week, and I raise it to the power 2.708, I'll get 15. Okay? I mean, let's do that. It's 2.718-ish to the power 2.708. Was it? So 15-ish. I'm rounding things up, so pretty close. So we only have 2 logarithmic buttons on the calculator. Natural log, that means base 10. Common log, that means base. Did I say natural log base 10? and then natural log base e, and the common log base 10. Nothing for base 2. So I'm still unable to answer this question. But before, let's just write down what we kind of discovered just by looking at our calculator, that we do have two special logarithms. So the common log, that means base 10. So we don't like to write log base 10 of x. That's just log of x. So again, that's 99% of the textbooks. If you don't see the base, that means base 10. And the other 1% of the textbooks, they'll just, who cares about base 10? That's made up. So it's all e. So log is just natural log. Anyways, don't worry. So boom. Don't see the base, that means base 10. So it has the same properties. If I ask you what is log of 1, what is log of 1? 0. And we can totally check this on our calculator. If I ask you 1 and I hit log, it will give me 0. If I do the other way, it will give me undefined. I cannot compute log of 0 because it's outside the domain. The domain of the logarithmic function is strictly positive. How about log of 10? What does that equal to? 1. And then log of 10 to the power x, that's x. And finally, 10 to the power log of x, x. Is that okay? So it's the same properties as I just listed for general base e. Now this is just for base 10. And we don't like writing base 10, so here we go. So that's the common log, so that's one button on your calculator. Now, another button is the natural log. So that's the log base e of x. We don't like writing that. That's ln of x. Natural log. So again, has the same properties. Natural log of 1 equals 0. Natural log of e equals 1. Natural log of e to the power x, that equals x. And e to the power natural log of x, that is also x. So how much sense did that make? It's just the same kind of property. So I can ask you some questions. I can ask you to evaluate log of 1 over 1,000. You can do that one without a calculator. You can think to what power to raise 10 to get 1 over 1,000. -3. But again, if I type this into my calculator, if I go, here is 1 over 1,000, I hit log, it's -3. Okay? But if I ask you to compute log of 37, so what power you need to raise 10 to get 37? Did I close my little calculator? Now you'll hit 37 and log, so whatever that number is. So that's something that you cannot do in your head, but your calculator will take care of that. So that's the power you need to raise 10 into to get 37, so whatever, 1.57. Right. I can ask you what is natural log of e to the power pi. But I can also ask you what is natural log of 0.13. I can plug that in the calculator now and hit natural log, so -2.04-ish. Is that right? So we only have those two buttons for now. that okay? But at least with these two buttons, I can solve some version of, I can do some damage. So we were playing with some investments last time, remember that? Louis had an investment opportunity. Remember your investment opportunity? You were paying us. So we get, I don't know, 7.25 continuous. So rate compounded continuously. Continuously, right? And what were we buying? You guys were buying us $800 snowboard, right? That was yours. Yeah, you were. You said, you didn't say so. You said snowboard. I remember that. That was you. I have a recording. I want to pull it up, and we'll do a voice recognition software. It was definitely you. Well, anyway, so we want to get 800. We only have, I don't know, how much do we have? 500. How long does it take? So basically, how long is it going to take to go from 500 to 800? And we were not able to solve that equation. Because if I set this up, remember the value equals the principal e to the power RT, so the PERT formula. The A is what we want, 800. P was 500. E, the rate is 0.0725. We convert percent to decimals times T. And that's the unknown. We want to solve for T. So the way we're going to solve these types of equations, first, I want to get rid of all those constants. I want to get exponential thing by itself. So I'll just, first thing I'm going to do, I will divide both sides by 500. So the 500 is just going to cancel. So this is E.0725T equals 8/5. Right? Okay. Why are you smiling? You know what I'm going to do next? Well, because again, I'm solving for that little t. So that would be really nice if that e would just disappear. If just that somehow that e would go away and I would be left with that exponent, it'll make it a very easy equation to solve, right? If I cover the exponent, that's a linear equation to solve for t, right? So do I have a property that has e to some power and then just leaves you with that power? I mean, what am I missing? What am I missing? See what I'm trying to do there? It would be really nice if I had a natural log in front of that. Wouldn't that be nice? Then the whole thing would just explode, and I would be left with just the exponent. So I'm taking the composition of a natural log, and the left-hand side of this equation, to keep things balanced, I will take the composition of a natural log and the right-hand side of that equation. And we can do that. One of the bigger reasons that we can do that is because natural logs are one-to-one functions. If it has one solution, I'm not, turning any other extra solutions. When we were squaring both sides, that's kind of the same thing. We're taking the composition of x squared of both sides. But by the property that I just wrote a minute ago, the left-hand side just explodes and gives me 0.0725t equals natural log of 8/5. Natural log of 8/5 is a constant that I can compute. I can plug it in my calculator. I have a natural log button. And all of a sudden, this is a linear equation, right? I have a constant times a variable equals some other constant. In order for me to solve for the variable, I need to divide both sides by the constant in front of that variable. So whatever that number is, it will tell me how many years it takes for $500 to grow into $700, no, $800 at 7.25 rate compounded continuously. So we can compute that. So it's 8/5, so that's 8/5, 1.6. Take natural log of that, so 0.47, and then divide that result by 0.0725, so about 6.5 years. You're still here? Oh. So 6.5 years. Questions? How we got that? Willie, any questions? Is that good? So using a PERT formula, present value, future value, solve for the variable that's all the way up on the exponent. It's a big day in your life, and we're not able to do that earlier. So basically, again, this is the power of the inverse. That's why we even bothered with the inverse. That's what I was showing you, how I can take composition of a function and its inverse and then just explode the whole thing and just leaves me with the guts. And we kind of wanted those guts. Turn the messy equation into linear equation. And we like linear equations. Is that good stuff? Yeah? All right, so let me give you the 3 more kind of properties, or what did I, okay, here are my rules of exponents. I kind of want them. So we wrote, oops, okay. We wrote our rules of exponents. I don't know if I can do them now. Because I have very similar rules for logarithms. Rules or laws, whatever you want to call them. So the equivalent of a product rule for the logarithms because the rules of exponents, these are my exponential functions. And the logarithms are the inverses of the exponential functions, and the logarithms are exponents. So if you just ask this, if you answer this question, what do we do with exponents when we multiply? We add exponents. So we're going to be adding logarithms if we multiply. So the equivalent of that rule would be if you have a log of a product, that becomes sum of logs. Logs are exponents. We add exponents when we multiply. Let me demonstrate this rule on a silly numerical example. Log base 2 of 32 is clearly 5, right? 2 to the power 5 equals 32. But let me ask you this. What times what equals 32? Can you break down 32 into product of two numbers? 8 and 4. So this is the same as log of 4 times 8, right? I want to see if we're going to be consistent. This rule suggests that this is the same as log base 2 of 4 plus log base 2 of 8, right? The product turns into a sum. Well, what is log base 2 of 4? 2. And what is log base 2 of 8? 3, and 2 plus 3, 5. That's not a proof, but hey. The way you prove this rule, you'll just raise a to the both sides of that equation, and then you use rules of logarithms, the earlier ones. A to the power log base a of whatever is whatever. That's one of our inverse properties. So the left-hand side is mn, right? While the right-hand side, let me play with that here. You have a to the power of a sum, and we know that we add exponents when we multiply. So if I see something to the power that has an addition, I can always think of that as a to the power log base a of m times a to the power log base a of n. I went from here to there, right? Just kind of working backwards, my rules of exponents. Well then, a to the power log base a of m is m, a to the power log base a of n is n, and the operation is a product, so mn equals mn. It's a weird kind of way of thinking about it. I just need you to buy what I'm selling. Are you buying what I'm selling? Okay, log of a product is the sum of logs. Just like exponents, when you multiply, you add exponents. So good, you don't need to know these little proofs. It's just more to convince you. The numerical example was kind of cute. I guess I'm losing it. Okay, so this is, whatever that is, the product rule. The quotient rule, well, what do you do with exponents when you divide? Subtract. So if you have logarithm of a quotient, that becomes difference of logarithm. So this becomes log base a of m minus log base a of n. How's that? Again, I can prove it in a similar way. I'm not going to. This is really similar to the quotient rule for the exponents. When we divide, we subtract exponents. And finally, the power rule. If I have log base a of n and just n raised to the power r. Not the whole thing, just a little n, like that. So what do we do with exponents when we raise power to a power? Multiply. So that little power r kind of comes down and turns into multiplication, right? R is a power, log base a of n is some other power, two exponents, and that's what happens. If you happen to watch that little video I posted on Canvas, you know why that's called the power rule. Why is that called the power rule? Oh, that is important. Oh, yeah, did you do the note cards? Yeah? That's good enough. So why did I call that the power rule? Okay, well, let's go slower then. Why did that was called the product rule? Why do you think this is called the product rule? Because there's some kind of a multiplication. So it's dealing with the products. Why is this called the quotient rule? Division. Why is this called the power rule? Because it's two powers, but I like to think, and this is my lame little joke, that this is the powerful rule. This gives you the power. Is powerful 1L or 2Ls? 1, really? But it's powerful. Huh? Powerful rule. Why that's important? 2x, 2 to the power x equals 7. Yes, I can rewrite it as the log base 2 of 7. Doesn't do me any good because my calculator does not have log base 2 button. But what button my calculator has? Log base 10 and log base e. So common log, natural log. I really like natural log. So what I could do, I can take this equation and I just take natural log of both sides. Right? I mean, you just saw me do that earlier. Now, by the power rule, if I have natural log of 2 to the power x, what happens with that x? What happens with that little power? Where can I put it? Yeah, it just kind of folds down. It turns into x times natural log of 2 equals natural log of 7. Linear equation, isn't it? That's a linear equation. So x equals natural log of 7 over natural log of 2. I can plug it in my calculator, and I will finally know to what power I need to raise 2 to get 7. So natural log of 7 divided by natural log of 2. So there we go. 2.81. Is that fair? 2.807. How about that? What was that? Well, the computation? Yeah. So again, this thing tells me natural log of 7 divided by natural log of 2. And I have the natural log button on my calculator. I don't know, do you have a calculator? Okay, so on your graphing one, you can just type it in. You just go ln 7 close parentheses divided ln 2 close parentheses. Now in my cheaper version of a calculator, I just have to work it backwards. So I go 7 and I compute natural log of that. It's natural log of 7 divided 2 natural log of that. So you see it does say ln of 7 over ln of 2 equal 2.807. So this means, again, what this means, if I take 2 and raise it to this power, I'll get something close to 7. Again, depending how many decimals I carry, the more accurate my results get. But 2 to the power 2.807, yeah, 6.998, that's close. So depending how close you want to be, that's how many decimals you carry. My math lab, I'm sure, will tell you how many decimals to round it to or whatever. So I don't need other buttons. I could have done the same thing with, by the way, I can do the same thing with the common log. It doesn't matter which log I use. If I have natural log, if I have 2 to the x equals 7, and I apply common log to both sides, because that's another button on my calculator, same thing happens. X falls down by that power rule, so this becomes x times log base, x times log of 2 equals log of 7, so x equals log of 7 over log of 2. So all the, the only difference between this expression and the one we just did with natural logs is that instead of natural logs I have a common log. So it doesn't matter which log you use as long as it's the same log. So if I type all of that in, 7 log of that divided by 2 log of that, it better be 2.807 with some junk. Yeah. So it doesn't matter which base of those logarithms as long as it's the same. Actually, this gives us what is called the change of base formula. Then I can take any log base a of x, just like we just computed log base 2 of 7, with doing that operation. So log base a of x equals log base b of x over log base b of a, where b is a free base, whatever you want. B is any base. So no reason to change log base 2 to log base 7, but definitely base 10 or base e, because that helps you with the computation. So this is the same as going natural log of x over natural log of a, same as going log of x over log of a, if you have some fixed bases. It's pretty easy to remember this formula. What I usually tell my students, the way I memorize this formula, the way we write the logarithms, that base kind of appears down below. So whatever the base is, it ends up down below. So as it's written, a is below x, so a is below x. This is an easy way to memorize this formula. Okay? So with this now, I can ask you to compute any logarithm of any base of any number. For example, I can ask you to evaluate log base 11 of 23.41. We can compute that by just going whichever log you prefer. I like natural log, going with natural log of 23.41 over natural log of 11. And I can plug this into my calculator and it will give me the answer. Okay, I only need that button really. So 23.441 natural log divided by 11 natural log equals whatever, 1.315. Okay, so that's 11 raised to that power is going to be 23.41-ish. I mean, if I raise it to that power precise, it's going to be exactly the same. Because of the rounding errors. Yeah, here we go. Cutting down on the rounding there. How much sense all of that makes? So we have change of base. Yeah, this I just covered sections 5.3 and 5.4. Well, not entirely. With section 5.4, we'll get into these types of examples. That's an important type of an operation. I can ask you to simplify logarithmic expressions. Meaning, you're starting with something messy, and you want to write it into the sum or difference of very simple logs. So starting with one log, one messy log into many simple logs. This is a 1. So what I mean by that, let's say we have log base 3 of x, y, z squared. Something like that. So that is a 1 messy log. I want to turn it into many little logs. So I know my rules. I know that log of a product turns into the sum of logs. So every product turns into an addition. So this becomes log base 3 of x plus log base 3 of y plus log base 3 of z squared. That's using the product rule. So log of a product turns into the sum of logs. Is that okay? Is there anything else I can do here? Is there any other rule of logs that I can apply to make it even simpler? I mean, can I do some of that little too? Yeah, I can bring it down. So now it's a linear combination of logs. It's just addition, no powers, log base 3 of y plus 2 log base 3 of z. So that's many little simple logs. Yeah, 2 times log base 3 of z. Is that okay? How about log base 2 of x over the square root of y times z, like that. So we're gonna, and again, you can take as many steps as you like here, but all I see right now, the big operation is division. And I know how to handle division. Log of a quotient becomes difference of logs. So I'm going to rewrite this as log base 2 of x minus log base 2 of the square root of y times z. Is that okay? Now, to move forward, because it feels that I should be able to deal with a product, that whole square root business stops me from getting into the product, because I don't want to see that square root here. Can I get rid of that square root? Well, I shouldn't be doing any of that, because I'm changing the problem then. But is there a way to rewrite the square root as a power? What exponents are equivalent to square roots? 1/2, right? The fractional powers are radical, so this is the same really as log base 2 of x minus log base 2 of yz raised to the power 1/2. And what can I do with that power by the rules of logarithms? If I have a little power, I can drop it down. So this becomes log base 2 of x minus 1/2 log base 2 of yz. Is that okay? So now I have log of a product. What's going to happen with that? What can I do with the log of a product? This is the first example. What products turn into? Well, be careful. So yeah, it becomes, but yeah, log base 2 of y plus log base 2 of z with 1/2 applies to both, right? Because 1/2 was multiplied by the entire thing, so 1/2 should be still multiplied by the entire thing. So when you distribute 1/2, you get 1/2 in front of each log, but negative in each case. You just distribute the negative 1/2. So you get negative 1/2 log base 2 of y minus 1/2 log base 2 of z. So the negative 1/2 distributed throughout the parentheses, yeah. No, because it's distributive property. It goes like that. Okay, because that negative 1/2 applied to the entire thing. So negative 1/2 should still apply to the entire thing. So that second sign changes as well. How's that? Yeah, that's basically, I really don't want to, when you get down to there's the no exponent type of parts, then we're done. Okay? Well, yeah. Well, because it's, you see, the important part would be to go backwards. If I give you this mess, can you put it all together into the single log? But it's, you want to know how to go both ways, so the important way is going to be easy. Because when you solve equations and you have a bunch of logs floating around, it's sometimes easier to put them together into a single log. Makes equation solving a little easier. So I'm not necessarily saying it's a simpler case, but all right, a trick question. Natural log of x plus 2. What can I do with that? Because again, it's not a product, it's natural log of. So it's a composition. Now, do we have any rules that tell us how to deal with a natural log or any log of a sum? We'll have a rule for a product. Product turns into sum, but natural log of a sum, nothing I can do. It's just natural log of a sum. I cannot split that up. There's nothing I can do with that. So kind of a trick question. Hence that little warning. So yeah, nothing I can do with that. So don't break it up into natural log of x plus natural log of 2 or whatever. Because let me just give you a numerical example. Don't write this down. But if I give you log base 2 of 16, that is 4. Do you all agree with that? But if I say that it's the same as saying log base 2 of 8 plus 8, right? That's 16. You agree with that? And if I decide to distribute log base 2 of 8 plus log base 2 of 8, well, that's 3 plus 3. And that's 6. Not the same as 4. Right? So that's wrong. So I'm getting different answers. And that shouldn't happen. So the log does not distribute through the sums or the differences. It can only deal with a product. Now, in lieu of my trick question, what can I do with that? I cannot break it into two logs. I cannot go natural log of x squared minus natural log of 4 based on what I just did here. I cannot bring that little 2 down because 2 is not applied to the entire expression on the inside. If this was like, if this whole thing was written like that, then yes, I can bring that 2 down because the whole thing is squared, and that becomes 2 natural log of x minus 4, and we're happy, okay, because we did something with this. And I cannot do anything with natural log of x minus 4. What was that? Oh, you mean change the base? Is that what you're talking about? Well, it's base e, but yeah, I mean, I can say that. So if this equals, but you're assuming then that this equals x. I'm not saying that. If I wrote it like that, then yeah, that would be like e to the x. Yeah, some other variable, so let's call it, I don't know, y. So yeah, this is equivalent to saying e to the power y equals x squared minus 4, but it's, that's kind of iffy. Yeah, I can definitely factor that, because again, remember, I can only deal with logs if they have products or the quotients, and the factoring will give me a product on the inside, right? That's really natural log of that product. And then the product can be turned into a sum. So this is probably as far as I can go with that one. Natural log of x minus 2 plus natural log of x plus 2. So the product can be turned into the sum, but if you start with the sum inside, there's not much you can do. That does not break down. This is just like saying, 2 to the power 3 plus 2 to the power 4. It's 2 to the power 3 plus 2 to the power 4. There's no simplification that you can do, right? Those are not like terms or whatever. All right, so this is one form of the exercises that you will be doing when you have one log and you're breaking it down into little logs. So that's called the expanding logarithmic equations. We can also go backwards. If I give you many little logs, we can put them together into one messy log. So let's call it, I don't know, contracting. So, for example, we have log base 4 of A plus log base 4 of B minus log base 4 of C. So I'm going backwards. What do you think is going to happen here? Using those rules / laws. Yeah, how? Squared. Why squared? Why is it A times B times C? Why you just multiply it all over? Because you said, yeah, I want to condense it. But why is it ABC? Why you decide to multiply all of them instead of doing something else maybe? AB over C. Addition becomes multiplication, subtraction becomes division. So really, everything with a plus ends up in the numerator, everything with a minus ends up in the denominator. So that will be AB over C. So yes, so that's how you would do that one. All the pluses go on the top, all the minuses go on the bottom. Okay? Well, yeah, but well, because if this was a plus, then yes.
So if you added another minus log base 4, like D, would you like do AB over C over D?
Well, no, it will just be, if I had it like that, and let's just mix it up. Let's make it log base A of log base 4 of A minus log base 4 of D minus log base 4 of C plus log base 4 of A. Then again, all the pluses will go on the top, all the minuses will go on the bottom, like that. Well, B. Shut up. Yeah. Again, the reason for that, I mean, there are some steps that we probably don't want to write out. Really what I'm doing in order to come up with that answer would be log base 4 of A plus log base 4 of B. And then with the negatives, I can factor the negative out, and then I have log base 4 of C plus log base 4 of D, right? So these two become a product, log base 4 of AB, minus these two become a product, log base 4 of CD. And then the minus puts the CD in the denominator. And then by the quotient rule, you end up with log base 4 of AB over CD. So this is going to happen every time. Pluses go on top, minuses go on the bottom. So you don't have to do all those extra steps. Does that make sense? Even if you do it, as you pointed out, AB over C over D, like that, well, that really means AB over C divided by D, right? Which is same as AB over C times 1 over D. So d still slides in the denominator. So you don't need multiple denominators. Pile all the minuses on the bottom. Is that okay? Yeah? Okay. Trying to think of a good problem. I know. Well, okay. How about log base 6 of 18 plus log base 6 of 2? I want you to compute, evaluate that value. We do not know, top of our head, what log base 6 of 18 is. I don't know to what power to raise 6 to get 18. I don't know to what power to raise 6 to get 2. I can use change base formula and compute all of them, and I'll get some weird answers. Or can I apply my laws to say this is the same as log base 6 of 18 times 2? Is that legal? And 18 times 2 is 36. And what is log base 2 of 36? I'm sorry, log base 6 of 36? 2. If I compute log base 6 of 18 and I compute log base 6 of 2 separately and I add them, I'll get 2. Is that okay? I mean, I don't want to do that, but I will anyways. Just to demonstrate. If I compute them separately, log base 6 of 18. If I use change of base formula, I have to go, let's say, natural log of 18 divided by natural log of 2. So, what? Let me try it again. I did something wrong. Natural log, yeah, I did something wrong. Natural log of 18 divided by natural log of 6. That's my change base formula. Yeah, that's better. So that's log base 6 of 18. I'm going to add it to my memory. I'm going to compute log base 6 of 2. So that's natural log of 2 divided by natural log of 6 equals that. So I'll add that to memory. And if I do recall, it should come out to be 2, right? Yeah. So, that worked. But of course, it's easier to use the laws to combine them. Yeah, well, you don't need to. How about this one? Log of x minus 3 logs of y plus 4 logs of z. Well, order of operation tells me to do first what I first need to multiply 3 by log of y and 4 by log of z. And the only way I know how to do that, I can toss those constants back on top as an exponent. So really, I'm doing everything backwards. This becomes log of x minus log of y cubed plus log of z to the power 4. So first, I'm going to throw those little powers back on top. So now I just have single logarithms. And then I can use my product or the quotient. So all the pluses go in the numerator, all the minuses go in the denominator. So this becomes log of x times z to the fourth over y cubed. So whatever's positive goes on the top, whatever's negative ends up in the denominator. How's that? Well, because it had a negative. So we're subtracting, that subtraction turns into division. Okay? Is that okay? Well, okay. Let me do another run of silly extra computations. Don't write any of that down. So this is where we're at. Log base x, can I write it as plus and then negative 1 times log of y cubed plus log of z to the fourth? Instead of writing a minus, I wrote it as a plus and then a negative. Is that okay? I mean, I'm just being silly. Now, so basically what I'm doing, I'm faking a coefficient in front. So again, by the rules, that coefficient can go all the way in the numerator. So this becomes log of x plus log of y to the negative third power plus log of z to the fourth. So all pluses, right? So all pluses then become products, x, y to the negative third power, z to the fourth. But we understand the negative powers are reciprocals. And this is a really messed up way of looking at this problem over y cubed. And you really don't want to be thinking like that. Just remember, the pluses go in the numerator, the minuses go in the denominator. Otherwise, it's weird. But these are, these are the reasons, because they can always manipulate that and stick with the basic rules. Is that okay? All right. How about this one? That's just 1/2 log, natural log of x plus 2 minus 1/3 natural log of x minus 2. So what's going to happen with the fractions 1/2 and 1/3? What are they going to become? Exponents. So as I'm throwing 1/2 on top, and I see some of you already miming the right operation that powers 1/2 and 1/3 are. What is the power of 1/2? So this is really natural log of square root of x plus 2. And what is the power of 1/3? Cube root. So that's a cube root of x minus 2. So that's how you deal with those coefficients. The coefficients go on top as exponents. And depending on what kind of exponents, you can always interpret them. If those are fractional, they become radicals. So subtraction becomes division. So we're done. 1 log. And we'll be doing a lot of that when solving equations. Because when you have many logarithms, it's actually going to be easy if we compact it into one. And that's section 5.5 and so forth. That's not going to get into the equations. So now I'm definitely done with section 5.4. So you're ready for the homework 12 and quiz. So I just put you ahead a day again. Not saying anything. I'll see you on Wednesday. Because those, we're going to really, the 5.5 solving equations and 5.6, all the word problems there are about this stuff. Yeah, we're really going to take our sweet time on that.